We tap a screen and a face appears from across the globe. We press a button and instantly stream a song. Underneath that smooth glass, a massive network of physical electrical gates handles the work, opening and closing billions of times per second to resolve every human command into a definitive state. To understand exactly how that hardware operates, we turn to digital electronics fundamentals. Presented by Mehul P. Gurnari at the AVPTI Technical Institute, the central question for the semester is, how does computer hardware think? This diagram illustrates the core operational loop used by every smartphone. A fingerprint provides the initial input. The central chip applies logic to evaluate that scan against stored memory. Finally, it grants access, providing the output. The physical world we live in is continuous, like the smooth red ramp on this graph showing analog signals. But a computer requires the absolute clarity of the discrete green steps. Think of raising a hand halfway. A machine cannot process halfway. It applies a strict threshold to decide, 0 or 1. Digital electronics fundamentals is the study of that translation, how we force the chaotic world of human experience into perfect binary decisions. This bar chart outlines the roadmap for the entire 30-hour semester. Over 5 specific units, you will acquire 5 distinct cognitive abilities: convert, apply, optimize, construct, and recognize. By the end, you will have theoretically built a computer's brain from scratch. The process starts with data in Unit 1. Because a physical circuit cannot read human language, we must encode every piece of information into a format the hardware can detect. This graphic shows how we encode decimal 13 into binary. Using a power of 2 weighting system, where blocks represent 8, 4, 2, and 1, we place a 1 in boxes that add up to 13. In the machine's language, 13 is 1101. This slide compares logic gates using real scenarios. An AND gate acts like a UPI payment. The pin must be correct and balance sufficient. The bottom left truth table shows it only outputs a 1 when inputs A and B are simultaneously true. With binary data and logic gates combined, a machine can evaluate its environment. However, wiring every single decision directly would result in a processor that is physically massive, slow, and highly inefficient. That brings us to Unit 3, efficiency. In engineering, a circuit must be reduced to the fewest possible gates to save electrical power and eliminate processing delays. This slide demonstrates simplifying complex circuits using a K-map. Think of it as Google Maps for logic. Instead of building the long, expensive equation at the top, the K-map finds a shorter route to the exact same output, BC plus AC prime. Once the circuits are optimized, we hit Unit 4, systems. A modern CPU handles millions of data signals at once. If they all tried to move simultaneously without a plan, the system would crash. To solve that routing problem, we use a multiplexer, or MUX. The railway analogy explains it best. Just as a busy station funnels many tracks onto one main line, a 4-to-1 MUX takes 4 input signals and directs them into one selected output path. At this stage, we have designed a highly efficient data-routing digital brain. But this brain only exists in the present moment. To make a system truly capable in Unit 5, we must account for history. We have to decide if the computer's output should depend purely on what is happening right now, or if it needs to remember what happened a second ago. This graphic compares those states. On the left is combinational logic, like a mixer grinder that runs only while you press the button. On the right is sequential logic, like a cricket scoreboard. To display the correct score, it must remember the previous delivery. Engineers use hardware units called flip-flops to achieve this. Each flip-flop stores a single bit of data, holding onto it until the system needs to reference that past state. By linking these stored moments together, we build circuits that can follow a sequence and track their own history. Adding memory is the final step in creating a system capable of complex multi-step operations. The practical lab milestones take those theoretical concepts and turn them into functional hardware. By the end of the term, you will have moved from simple textbook diagrams to building physical devices, like a smart room light or a digital quiz lock. This slide breaks down the 150-mark assessment. Manage it using the 3-round method. Understand concepts, attempt problems blindly, then rewrite missing steps. For a perfect exam response, follow the structural formula at the bottom: definition, diagram, truth table, expression, and finally the working steps. When you enter the lab, you are adopting the mindset of an engineer. If a circuit fails to turn on, you have simply gathered new data. Debugging that failure is the process through which you actually learn. This exit ticket slide leaves you with a challenge. Identify one digital device you use today and map out its primary input and output. If you have any questions, ask them immediately. Prashna hoy tu teret pucho.